The way of success is the way of continuous pursuit of knowledge. Very good morning to one and all assembled here. I am Nikhil MC, 7th Sem ECE, take privilege in anchoring this event, and it's my pleasure to welcome you all to this IEEE technical event, Aikya 2023. Let's invoke the event with the blessings of Almighty by an invocation song. May I request Yashaswini and Bona to sing the invocation song. Thank you, Yashaswini and Bona. Now, we will have lamp lighting ceremony to mark as a tribute to the Lord Almighty. I request all the dignitaries on the dais to light the lamp and inaugurate this event. I also request all the dignitaries to pay the floral tribute to our founder chairman, Dr. S. M. Venkatapati sir.
शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते
Thank you, all dignitaries. My hearty welcome to our Honorable Chairperson, Srimati B.L. Ramadevi Venkatapati Ma'am, and CEOs of East Point Group of Institution, Shri S.P. Pramod Gowda Sir and Shri S.P. Rajiv Gowda Sir in their absentia, but they are conveyed their best wishes. I also extend a warm welcome to our Senior Vice President of EPGI, Dr. Prakash Yes Sir, in his absentia. I extend a warm welcome to today's chief guest, Dr. P. Venkatesh Rao Sir, Scientist G, Center for Airborne System, DRDO, Ministry of Defense, Bengaluru. My hearty welcome to you, sir. I request our Vice Principal and Lecturer, Dr. Yogesh G. Sir, to hand over the bouquet. My hearty welcome to our beloved principal, Dr. Mrutyunjay V. Latte, sir, who is a dynamic person with great ideology and vision. We hope that with your energy, enthusiasm, and focus on education and learning, our institute achieves the greater excellence. Under your leadership and guidance, may we reach the next levels of glory. I, on behalf of EPC department, welcome you, sir. I request IEEE Student Branch President of EPCT, Mr. Sudhanshu, to hand over the bouquet. My hearty welcome to our beloved Vice Principal and HOD, Dr. Yogesh G. Sir, who has been leading the EC department with his good leadership qualities. Good leadership makes every task easier and the hardest task possible. With your direction and guidance, definitely our department will achieve the greatest heights, sir. Welcome you, sir. I request IEEE 10th Student Branch President of EPCT, Mr. Sudarshan, to hand over the bouquet. I extend a warm welcome to Dr. Manimozi I, ma'am, HOD of CSE Department. My hearty welcome to you, ma'am. I request IEEE Student Branch Vice President of EPCD, Mr. Akash Pandit, to hand over the bouquet. I extend my warm welcome to IEEE Branch Councillor, Professor Kiran Kumar K. Sir. I welcome you, sir. I request Ms. Bona to hand over the bouquet. I also extend my warm welcome to IEEE 10's Coordinator, Professor Wasim Yasin, sir. I welcome you, sir. I request IEEE Student Branch Treasurer of EPCT, Mr. Siddhalinga Swami, to hand over the bouquet. I welcome HODs of all department and faculty members on this occasion. I welcome all the participants from various colleges who are part of this event and have contributed in making this event beautiful. Once again, I welcome you all. May I now call upon IEEE Student Branch President of EPCT, Mr. Sudhanshu, to deliver the presidential speech.
Good morning, everyone. My name is Sudhanshu, President of IEEE Student Branch EPCT. Aikya is a national level tech fest happening since 2018. Various technical events have been organized in where various departments and various colleges participate here, like robo race, project presentation, etc. This is a platform for students. Aikya event is conducted every year and under the banner of East Point IEEE Student Branch and IEEE TEMS, in which there are 50 to 100 members in our IEEE branch in our college. The branch counselor of EPISB is Professor Kiran Kumar K, Assistant Professor of ECE, and Professor Wasim Yasin, Assistant Professor of CSE. I would like to say today's events which are being organized today, that are Robo Olympics, where the participants bring out their line following robot to compete in this event. Code Battle, where the participants show their coding skills in the event by solving the problem statements which will be provided by the team coordinators. Solution for Pollution, where the participants will be showing up their ideas to prevent the upcoming social problems in pollution. design matrix, where the participants will be showing their HTML coding design, website designing using AI also. Mind Sprint is a technical quiz in which technically related questions will be asked. AR Treasure Hunt. AR Treasure Hunt, you might be knowing Treasure Hunt game, right? In which augmented reality, we will be using augmented reality technology to play this game. TechMind Fusion. This is a project presentation where different technical projects and the posters are presented. And Bytebuster. This is a debate competition which will be on topic of technologies. And that's it. Thank you. And all the very best for all the participants. Hope you get the best.
Thank you, Sudhanshu. I request our respected principal sir to say a few words about this event.
Good morning, everyone. Dr. Venkatesh, respected chief guest of the today's program, Dr. Yogesh, Dr. Manimoji, all my colleagues, students, and the IEEE chapter associates, all the representatives. At the outset, congratulations for having initiated this competition and the involvement of students for all the activities, the competitions we have just now listed out. And this is being conducted every year at East Point College of Engineering and Technology. I understand that it is fourth in the series. Good thought process. Please keep it up, and definitely this one day events are going to throw light on many new things in the design or in the competition process, and it is going to ignite the young minds and competitive spirit among the students and among the participants. So I also understand large number of students for all the events have registered for this. And I wish everyone all the best, and such competitive programs are very essential to ensure that the campus is in a vibrant mode all time. And this is a technology era wherein each and every issue or every item can be seen association with the technology, and we can include or we can think of new designs, new processes are being identified, and it is going to give you a lot of ideas, and that is how you are required to what we call in the today's requirement upskill your thought process and reskill your thought process. So I wish everyone all the best, and also congratulate the organizers of the IEEE chapter at EPCET for having initiated this program. Thank you.
Thank you, sir. I would like to call upon Professor Kiran Kumar sir to introduce the chief guest.
Respected dignitaries on the dais and off the dais, and all respected HODs and faculty members, and my dear students. So it's a great privilege to honor to me to introduce such a great personality and scientist of DRDO, Dr. P.V. Rao sir. So P.V. Rao sir has completed his diploma in DT Telecommunication Engineering in the year of 1980. And he holds a bachelor degree in electronics and communication engineering from Bangalore University in 1989. And he holds a master's of MSc engineering from Indian Institute of Sciences from the year 1993. And also he has a doctoral degree from Indian Institute of Science in 2000. So sir has a lot of experience. His area of specializations are in antenna arrays, RF design and development, microwave communication, and radar systems. Sir is currently working on is the chief scientist, scientist G for Center of Airborne Systems at DRDO, with Ministry of Defense. So he also has worked as a faculty in engineering colleges, and he has taught instrumental in getting the postgraduate MTech course in digital communication to the telecommunication engineering department, which is accredited by the telecommunication department of MSRIT, Bengaluru. And also he served as a member of board of studies of post-graduation of MSRIT UBC Engineering College. He also guided the undergraduate projects and research fellows and senior research fellows, and also postgraduate students. So, in his credit, he has a few awards. He was awarded with the Director's Special Award for the contribution towards the design and development of ACSA, and also Technology Group Award for the development of ESA, and also IETE MN Saha Memorial Award for the Orient paper published, which is based on this topic. And also he was the Lab Scientist of the Year, awarded successfully for the completion of the design, development, and integrating testing of AES with airborne radar. And other responsibilities, he had so many during his tenure as a research scientist G in DRDO. He was also deputed to the few countries abroad. In 2006, he visited Israel, and also in 2013, he visited Germany for research and developing the consultancy with the few companies. And he's also fellow of IST and a senior member of IEEE and secretary IEEE ASS Council, Bangalore chapter. Lot more things to describe sir, because sir has briefed his profile and shared us. So sir, today we are very glad and privileged to have you, sir. We welcome you. Thank you.
Thank you, sir. I request our chief guest, Dr. P.V. Rao, sir, to share a few words about this event.
Thanks for a nice introduction, Professor Kiran. Ladies and gentlemen, it gives me a great pleasure in participating in your test fest. The technical discussion opens up unknown or missed knowledge. Mutual discussion brings everyone to same platform. Focused and constructive discussion becomes the learning. Knowledge is like ocean. It is learned by active participation, discussions, and performance. Major amount of exposure happens through interaction and attending such events. One has to utilize every opportunity which they come across and involve completely on the subject he has been exposed. Fix a goal or ambition to self. Dedicated, devoted, relentless efforts is essential to achieve the aspired goal. This would give immense happiness and contentment to the individual. The impediments based should not be distract the focus. Small failures should be assessed properly to obtain a proper workable solution to or remedies. One should never give up the desired goals till it is completed. Failure teaches the missed right approaches and teaches not to repeat the same. Assessment of the failure is essential for the future improvement. Try to adopt patience, perseverance, focus, dedication, group activities. I wish you all success in your future endeavor. So this I wanted to share because these are the things what I followed in my career. Whether it may be in ISC, Indian Institute of Science, I worked as a RA and all that kind of thing. And there also I could manage different heights because of that. And same thing adopted in the DRDO also. And wherein we successfully completed the Netra. And in fact, that Netra participated in Balakot strike. So that is how we have that credibility and we have successfully completed that project. So I wish you all a great success, and it's a nice event, whatever you arrange. And I saw that events, whatever followed after this inaugural function, and I wish you all success.
Thank you, sir. I would like to call upon Vice Principal and HOD Dr. Yogi sir to address the gathering.
Very good morning. ಎಲ್ಲರಿಗೂ ನನ್ನ ನಮಸ್ಕಾರಗಳು. It's a great privilege and honor to speak on this occasion. Respected dignitaries on the dais, Principal Sir, Rao Sir, Manimuji Madam, respected head of the departments, respected faculty members, and my dear student friends from the various institutes across India, and my dear student friends of East Point campus. It's a privilege to have such type of events in our campus. Recently, we had Chandrayana. This particular event made the whole world look towards India. It's a proud moment as an Indian. See, these type of events will ignite all of us as young engineers. And you are the future engineers. You should carry over those type of events in the future. If you want to, make such great impactful events, these type of technical fest definitely act as a platform. Dear students, when you think out of box, you come across with innovative ideas or innovative products. Once, if you get an innovative product, the next question is how to go about, how to sell about. See, for that, you need a proper networking. See, each and everything has its own importance, dear students. You should understand this. That networking can be done with this type of, technical fest. If you want to come up with a very good product, you should have a good competency level. See, that competency level is also able to be managed with this type of events. I'm very grateful to Mr. Kiran Kumar, IEEE student branch counselor, and also to the WASIM IEEE Times branch counselor. Let us have a big round of applause for them. My sincere thanks goes to President of Student IEEE Student Branch, Mr. Sudhanshu, and his whole executive team. They have worked day and night to this event to happen in a very better way. Let me have a big round of applause for that. We have a plethora of events here. The first event which I would like to mention is code battle. This has been taken care by our honorable head of the department, computer science, and she was the brain behind initiating IEEE TEMS. With her whole team, she's taking care of the code battle. Let me have a big round of applause for her and her whole team. Next, we have a solution for pollution. This is taken care by under the leadership of our Nagaraj Sitaram sir, head of the department civil, and his whole team. Let me have a big round of applause for them. Next, we have AR treasure hunt. This is a bit of a different innovative idea. We do have a general treasure hunt, but student come up with an innovative idea of AR treasure hunt. This has been conducted by Honorable IS HOD, Professor Kempraj sir and his team. Let me have a big round of applause for them. In the same way, Department of Electronics is taking care of Robo Olympics under the leadership of Dr. Jayanti Madam, and under the leadership of Dr. Chandrappa, the Bites and Busters and Mindspread. Let me have a big round of applause for them and their team. Dear students, kindly utilize this opportunity for a betterment of your individuals. Definitely, this type of events will make you to grow in your career in a better way. I sincerely thank all the participants from various colleges. I'd like to mention here that around 119 registrations have happened. It's a proud moment for all of us. In fact, when we started the registration, Kiran Kumar used to update me every day. I used to see the progressive increase in the count. Even yesterday till 5 p.m., we had a huge rush at the fag end. That usually happens. But really, thankful to the whole team of Aikya, they have made it the count of 190, and around 11 colleges have participated. So with this brief thing, I would like to log off. I wish you all the best for the participants. Thank you, everyone.
Thank you, sir. Now I request the dignitaries to occupy the front row.
Ten, nine, eight, seven, six, five, four, three, two, one, zero.
Wow, it was such a nice video. I would like to tell all the very best to the participants for this event. Now, I request our chief guest, PV Rao sir, to take over the session.
online payment fund.
ಆಕಾಶ್
So good morning, everyone. I thought I would like to, because since it's a tech fest, I thought I'd like to share the kind of activity what we did towards airborne radar, and whatever the system we developed in CAPS, DRDO. It is achievement is like 6 countries in the entire world have achieved similar kind of feat. And we have done in DRDO indigenously, completely indigenous, and design, development, everything is done by DRDO with the help of industry partners. Of course, and they're all Indian-based industry partners. So basically, radar is taken from the batch principle, and whatever the ultrasound signal bat produces and find out the prey, and it will also find out the distance orientation of the prey, and whether it is a live object or a all that it can find out, and finally it catches the prey. And similar thing what we adopted in using electromagnetics, we have different kind of finding out the target. So the target I have only shown the nose part of the target. Nose part of the target. I mean, it's a part of the aircraft basically. It's the indigenous aircraft again. I mean, it's a fighter aircraft whatever India has produced. And we have concept of there is a transmitter and a receiver, and electromagnetic signal is fast. I mean, it's, sort of radiated towards the target, and the reflection whatever comes from the target is okay. Okay, reflection whatever comes from the target is picked up from the this unit whatever you have. I'll exhaustively cover the unit configuration in the later slides. And this, if the transmitter and receiver is located in the same position, is called as the monostatic mode of operation. And if the transmitter and receiver is located in different location, it is called as the bistatic. RCS is a different nomenclature. I mean, don't worry about that. It's a monostatic radar and is a bistatic radar. And most of this ATC, whatever you see to find out the target, I mean, flying aircrafts in the thing and all that, and to guide, they use monostatic radars. And there are two kinds of radars. One is a ground-based radar and the airborne radar. And the ground-based radar has the limit of horizon. Because Earth is a curved body, and 60 kilometers is the distance what you will get the curvature of the Earth. So the LOS whatever you have is up to 60 kilometers only. That is why whatever you see this beam is lifted up. So this is the radar. I mean, this is the front radiating surface, and this is the coverage of the radar basically. And whatever the target which is coming in that within that vicinity is detected and sort of presented to the operator. And the why airborne radar is one question mark comes actually. I told you that this is a ground-based radar, and it has a vision only in the elevation like that. And suppose a target, the low flying, I mean any targets. So nowadays fighter aircraft comes at a very low level actually, to the tune of about 2 to 3 kilometer height, and which will get unnoticed till this point. So it is already about 60 kilometer ahead and all that kind of thing. Any corrective measure somebody want to take care to counter the fighter aircraft, they will not have enough time. So for that reason, what we do is that you put the radar in the flying platform, as a aircraft and all that kind of thing, and the vision will be down like this. It will cover 200 kilometers in the enemy territory as such. So that is the objective. Basically, even a low flying object or any obscured terrain also, you can find out the target flying and all that, and it will cover the elevation. This is only azimuthal coverage I have shown it in this domain, and this is the Earth basically. This is the Earth profile, whatever you see. So our objective is to make a radar, airborne radar, and put it on the aircraft and make it operational. So the airborne radar actually started with the front radar. This is every fighter aircraft carries this serpent radar. Basically, it's only to track the enemy what do you call aircraft. And once you track, and basically you want to when you go for a fight between aircraft, fighter aircraft, another enemy fighter aircraft, they have to track that and put the missile towards that. So that's the essential part. So the front end we have radar. Basically, this is a mechanically steered antenna, and this is also mechanically steered antenna. This is another type of mechanical steered antenna. And then you have it's a planar array. So since you are all EC department guys, you will come across antennas, RF antennas, and all the kind of the benefit of array antenna. I'll show subsequent slide. So basically, it is a partial mechanical plus a kind of scanning of. Beam is formed by array of antenna. And then came is the concept of active array. So the active array makes you happen. There is no mechanical movement. It is only that the beam is shifted by electronic mode. I mean by just commanding. So our objective was to develop that active array on the platform of for the AWMC. I mean Netra, whatever we have. And basically what you have is that front end is a mechanical scan antenna. You have a transmitter and you have a receiver. So radar has both the thing, transmitter and receiver. So you send the signal, reflected back signal is collected and make the go through the receiver section and down convert and all that kind of thing. You do a processing and do basically radar processing you do and find out the targets. So you can identify the target, its speed, its direction of arrival or range, everything can be found out right, by this radar. And in active array, you have no mechanical movement. I mean, no mechanical scanning. It's a stationed array of antennas, and you do vary the phase of excitation of each element to get the scanning part. So why ASA is a question mark? So mechanical movement is always restricted. It's defined by the motor, whatever kind of thing you are using, and the mechanical restrictions are there as such. So for that reason, mechanical not the advantageous to go for simultaneous operation. Basically, you have surveillance as well as tracking. Suppose you want to do, it is not possible with a mechanical scan. So it can do only either surveillance or a scanning. I mean, surveillance or tracking. So not both. So in active area, what happens is I can keep multiple beam. I can look for a missile which is coming, or I can guide that. Track update rate is 1 second. You can achieve also, and you can put null in different direction and all that kind of thing. So many things can be possible. You can put a search mode. You can put a track mode. And it happens very quickly. I'll show you subsequently that at what rate you can do the this object. You can achieve the beam shifting and all that kind of thing. You can achieve within microseconds. So that is the kind of advantage what you have in the active array. So I was telling about that when you have an array, you can control with the weighting vector and all that kind of thing. Basically, you change the phase and the attenuation of each element, and you can shape the beam. So the beam, suppose I have not weighted, the beam will be like this. And suppose there is a jammer who is coming from here, I can put a null in that direction. So that means I cannot, it will not disrupt my operation of the radar. So that is how you can shape the beam and all that kind of thing. That is possible only in the active array. And you can even range coverage also. I can enhance it by control of some other parameter on the antenna array. So that is how you have a long range coverage. It's a long range coverage and a shorter range coverage, but wider angle of coverage. So these things are possible with the active array. And basically, I just want to, you would have studied in your engineering this thing actually that there are different kind of arrays. It's a linear array, the planar array. The reason behind, the linear array is controlled by a phase shifter. It's a variable phase shifter, variable attenuator. All the signal is summed up and then fed to the receiver system or a transmitter system. So by having this phase shifter and attenuator, what you have is you can shift the beam, main beam, in different directions. Say, suppose some weighting factor, you have the beam in this direction. This main beam is in this direction. By changing the weighting vector, I can have the main beam in 30-degree direction. This is all for linear array. That's why you'll see one main beam here, another main beam here. There's a back lobe, we call it as. And in the 60-degree shift, the main beam is shifted to the 60-degree. So like that, I can shift the main beam in the direction, whatever, I mean, whichever the direction you want. And this all happens through electronically. I mean, you just give a command, I will do the objective. It will meet the objective. And in 3D, I am shown the same thing. It's oriented in 90-degree direction. Same thing I showed is how the 3D looks in the what do you call in the space. I mean, the antenna radiation happens in this way actually. So why airborne? I mean, we not only have primary radar on the basically radar. We call it the primary radar. Its objective is surveillance as well as tracking. It will be flying in about 50 kilometers inside the enemy territory and look for all the airborne targets and or taxiing targets. I mean, the target which is just taking off also you can find out, and it will be looking at the enemy territory, whichever the side it is in, and all that kind of thing. So this is basically a radar what you have. This is a front-end radiating interface, whatever you have, and the target whatever is coming, I can figure out. I mean, I can find out, and yeah, I can keep tracking also. So if by just electronically shifting the beam, it is possible. And whatever the information is there, you would want to pass it on to the ground station. Basically, some of the operators will be sitting in the or major decision makers will be sitting in some room on the ground. So that is conveyed through a different communication system. There's a KBDL, K-band data link system. That's a SATCOM thing. From here, the data will go to the satellite and it comes to the down there. And you would like to guide our own aircrafts. That's what happened in the Malakot strike. The target, whatever was intended to go and to put the bomb on the location, it was guided by our aircraft. So what they did is they find out the track of our target, our aircraft. And similarly, you want to know whether there is a counterattack. When you are flying and all that, you have to look for the counterattack also. In case there is a counterattack, you have to inform to that our own aircraft to say that there are somebody is coming in this direction and all that. You take care of them also. So this is exactly essential when you are doing this kind of operation. And it effectively did that, and that is done through. I mean, our own aircraft is communicated through VHF line. This is a communication line as such. So these are all possible to have, basically advances came from the following drivers. So denser target population, you have huge amount of aircrafts flying nowadays. I mean, you need to have an account of who are all in the airborne, and you have to figure out where they are coming from. Because say when you are in airborne, I mean, you'll not know where you are. I mean, basically every aircraft will not know where they are. They have to be guided by the ground-based radar only. There is no other choice they have. Otherwise, they have GPS, no doubt about that. But GPS also doesn't give that much of information what they would have got from the ground station. So that is essential actually. So there are some more sophisticated DCCM feature. Basically, countermeasure we call it as. The countermeasure basically, suppose somebody is jamming me. I should have method of coming out of the jamming and continue with my objective. Our basic objective is to find out the target and find out the range, in which direction it's coming, which range they are in. And suppose some intended target is coming to, put a bomb in a city or something like that. Suppose I have this feature, I can figure out, yes, there is an enemy target. You can find out there is the target which is coming is an enemy or a friend or a foe. So it has several schemes for that actually. There's the IFF, ESM, electronic support measure, communication support measure. You can find out in fighter aircraft. So that kind of intelligence already is there in the system. So we have multi-mode operation and beam pointing agility. I told you the electronic scanning, what you call active electronically scanning. You have beam agility. I can shoot the beam quickly in any direction. So you can put the beam forming. Beam forming is basically, I told you how to avoid the jammer. So that is exactly what is achieved by beamforming flexibility. I can shape the beam in whatever the way you want. So, and most sophisticated detection tracking algorithms are also there actually. See now, suppose you have aircraft with minimum RCS and all that kind of thing, you can find out by a sophisticated algorithm. You know, moving, whether it is a moving target, it is a fixed target, all that information I can get it actually. And you can, many of the the algorithm helps me even identify which kind of aircraft is flying, whether it's a Sukhoi, it's a F-16 or whatever kind of thing. I mean, you can to that level you can identify the targets. And a lot of solid state, the advantages we had taken actually, because earlier we used to work with waveguides and all, I mean waveguides and tubes technology. It can be magnetron, klystron, or whatever kind of thing, and that had a limitation. So nowadays we have gallium arsenide, gallium nitride, MMICs are there, were very small, a compact and all that kind of thing. Utilizing that, we can achieve the objective. Same thing I already repeated, and I just wanted to share what is the ASA front-looking kind of thing has several things. There is a RF component, there is a TR module. So this is the radiating front end, and back with the TR module, there is an amplifier in the transmit path and the receiver path. And these amplifiers are distributed. For every element, you have an amplifier for transmit and a receiver. So the advantage of this distributed amplifier and all that kind of thing, I'll cover in the subsequent slide. And there is an electronics. Basically, mechanical support structure is essential, and there is a control system is out there. There is a FPGA and all that kind of thing used for controlling every aspect. I mean, every parameter of the TR module. The TR module, what we call is a transmit receive module, which has phase shifter and attenuator. Whatever I showed for every element, variable attenuator and phase shifter, that can be electronically controlled. Basically, digital commands will give and all that kind of thing, and they will perform according to our requirement. So the one what you would have seen in Aero India and all that kind of thing, our aircraft is always positioned there, and they'll fly also. And it has the top one box. It's called as the AESA, Active Electronically Scanned Array, and that is where we have this kind of system. It's a radiating front-end interface, and back-end all the RF systems are there. TR module. Every element needs a TR module. Every element requires a amplifier in the transmit path and receive path, and a phase shifter and attenuator. Like that is the essential. The entire box contains all these electronics and complete chain of the microwave system. And this is exactly what is contained in the entire box. It's a 1.5 ton weighing system with so much of electronics behind that. So you have front-end radiating interface, and you have TR module, set of them. Every element of this is supported by a TR module, and the TR module is an active device, and it requires a power supply and all that kind of thing. That is done by this, and the combining of all the RF signal is through several stages it is achieved actually. And we also would like to have health monitoring of the entire TR module what we have, because we need to know on the fly whether the TR module is working, or it is any problems are there and all that kind of thing. That health monitoring is achieved through this byte network. So basically, why we migrated to array rather than having a single mechanical structure? One is agility, I told you. Other thing is that there is a concept of graceful degradation. If one few elements in the array, suppose they are not working, what is my this thing? I mean, loss, or whether my objective will be met or not. That I need to have an a priori information. So that is seen by this. Suppose this is basically an antenna pattern, we call it as, this is a coverage, this is a main beam, and it's like torch light. So you imagine this is a torch front, and the other side you don't have any, because the torch light will focus only in one particular area. So rest all nothing will be there. So this is exactly what you see the side lobe, we call it as, and the side lobe level is very small. And when I have 5 failed modules out of some thousand odd, 1,500 elements, suppose 5 fail or 20 fail, how the silo will come up? So this is the 100 failed is so much of silo, but still main lobe is intact. So that is the objective of is this we call it as a graceful degradation. So, but in mechanical scan, what happens is suppose I have a single amplifier connected to the antenna. If that amplifier fails, it is doomed. I mean, everything is gone. So that advantage what you get with the distributed amplifier system, that is called it as active array. And these are all, again, the objective of our. And when you go for airborne radar, and you are putting that antenna system, active array on top of the aircraft. When you are putting on the aircraft, so much of technology, these things you have to take it. The technology, whatever you have, is since it has to fly. There is a huge amount of air force and all that, aerodynamic dynamical force and all that will be there as such. So those things has to be studied. Otherwise, what happens is the impact of the force is such that the whole dome, the whole structure should not fly out. It will not, should not, break and all that. So we have mechanical study to be done, environmental study also, because so much of electrons are used. The environment is changing from very hot to the cold and all that kind of thing. When you are flying up in the air about 11-kilometer height, the temperature outside will be minus 15 degree. Minus 50 degree. So that kind of temperature, and when it is on the ground, it will be say, whatever the environmental set temperature, 25 degree, 50 degree, depending on the terrain where you are working with. So it has to take care of environmental this thing also. Structural design has to be taken care, thermal design has to be taken care. We have digital software, microwave, because digital control is the one which is helps me to do command in through a computer. So that is the objective. What you advantage what you take out of digital this thing. And the aerodynamical study has to be done. Electrical, because power requirement is also there, that has to be studied. And this is the different stages of achievement is there actually. The involvement is there. So you have to do a priori to come out with this design. You have to do structural analysis, model analysis for the structure. Then only I can ensure that it is structurally rigid and it is not going to pop off by all these forces it is acting on that. So you have to do a buckling analysis, CFD analysis. A lot of mechanical analysis is essential. Similarly, electronics and electromagnetics analysis has to be done before we really, and all this whatever you do has to be certified by different qualifying agencies. Structural agency is different, electromagnetics or RF or instrumental agency is different. So when you design, what all parameter is required to be sort of taken care for the design. So one is the frequency of operation is essential. What is the polarization? Whether it is horizontally polarized, vertically polarized, that is the essential. And the electronic scanning limits. Now, when you go for a planar array, you have limits of scanning, because as you scan, electronically, the aperture size will reduce actually. Because it's an effective aperture size, what you call it as, it keeps on reducing. So that limits my scanning limit. Scanning angles. So what is the kind of directivity you are looking for? Accordingly you can design number of elements in the azimuth or elevation or whatever kind of thing. And what is the kind of radiated power you want from the AS? Active array. So, and another thing what we look for is the beam width of the main beam. That is in azimuth, elevation, side lobe level control also is required, because I don't want somebody entering from the side lobe. Information return is coming from the side lobe, and I don't know. I'll be misguided about the direction of arrival. So all these things are essential for the design of this thing. And this is how the entire system is realized, and the different LRUs, we call it as LRUs, line replaceable unit, because maintenance ke liye you need to remove them in case there is a problem and all that, you have to remove them and attend and put it back. So all this is shown, these whatever gadgets are shown, these are the realized one which are installed and running also. And basically, I'm shown all the LRAs which are existing in the our radar. This is the antenna, front end antenna. It looks like a slotted antenna we have actually. This is a cavity back slot antenna we call it as. And it's an integrated this thing. We have two kind of antennas, one for primary radar and there's a secondary surveillance radar we call it as. Is the information friend or foe is found out by having this antennas. So the antenna design, how it looks like, this is an open-ended waveguide thing, and it's a probe is fed and all that kind of thing. And these are the patterns what you get. It's a simple single antenna has azimuthal pattern, whatever you see there, and elevation pattern. And this is very essential to achieve the scanning limits. So that is where the design becomes very critical and all that kind of thing. And the similar exercise was done for the IFF array, I mean IFF element also. There is a device called the TR module. That is the heart of the entire active array. So TR module has a transmit amplifier and a LNA. There's a low noise amplifier in the receive. These are essential actually when you want to have low noise. I mean the noise being lesser is advantageous to meet the longer range. Suppose I want to have a range of the target to be identified at 200, 300 kilometer. You have spatial losses also. You know, 1 over 4 pi r square in that domain, the electromagnetic signal will experience a loss. So those things has to be countered. So that the only way I can enhance the range is by just having the low noise amplifier. So all this, and I need to put required phase shifter. So that it's a distally controlled phase shifter and all that kind of thing has to be incorporated in the TR module. And these, phase shifter and attenuator is a selective way of operational of these phase shifter and attenuator. I can achieve the beam shaping, that is basically keeping the side lobe as low as possible, and I can also achieve scanning of the main beam. That is, I'll show you subsequently how it is done, etc. So the TR module has several. See, what we have is there are number of elements in a particular column. So the entire all these elements are powered by one TR module. Every element is powered by one TR module. So there are 4 TR module here and another 4 the other side. Basically, we had 8 elements in the vertical direction. So all these 8 elements were powered exactly by the TR module. And I just wanted to share that the RF signal, whatever is coming here, how it is divided to 4. Several stages of the electronic system is there to come. I mean, to feed to the 4 element from the upper and 4 element from the lower. That is how you achieve the powering the entire vertical elements. And this is some, again, design constraints are there actually. So, every device when I want to sort of design, I need these are the parameters essential. So that for every design there are some parameters. For TR model, these are the parameters what I look for. And there is a pulsed mode of radar operation. That's why pulse width is essential. What is the duty cycle? Is on period, off period, and the pulse width matters a lot for the near range detection. If I have broader pulse, near range, till that pulse radiation happens, I'll not be able to get the reflected back signal. Because normally what happens is the pulse on period is used for the transmit of RF signal and off period is used for the receive of the signal. So near range detection becomes a hindrance if I have wider pulse. And wider pulse is essential to collect enough signal from the return signal. So all this matters a lot and all that kind of thing in the design. And I was talking about phase shifter and how we achieved is that the input is given here. There is a digital phase shifter in the common part, and attenuator is here, 6-bit phase shifter, and there is a DP. I mean switch. This is the transmit path, and this is the receive path. And the circulator is the same. What you call system is bifurcated by judiciously using the different RF devices and all that kind of thing, and you are able to achieve the objective. And they are all controlled by some controller is there, that is a FPGA based, and you can, why we went for FPGA is basically you have liberty to program them. Today I need to put this feature, I program in some way, and I need to put another feature, I can program in a different way. So that flexibility I can enjoy by having this FPGA. And what it does, I mean, the FPGA has an IO kind of thing for all these, phase shift alternator and switch and all that kind of thing, whatever you have. This is different, that after you realize you need to test them. You should have whether that an alternation is doing properly by the command and all that. Whatever selected alternation value, is it happening or not? These are the different testing process what you followed to say that PR model is meeting my objective. And another thing is that these are the dissipative device. I mean, it has a lot of dissipative device in the TPR module. I need to pull them. I mean, otherwise the functional aspect will be different with heating whatever you have. So how do you do that? We calculated what is the kind of uh, the airflow, I mean cold airflow or airflow will help me in reducing the temperature of the surface temperature of the TR module. That one study we had done by analysis only, and that was measured also, and it is meeting. And the inlet, whatever the box I showed, that the inlet is air comes from the while flying itself. I don't put a extra air for that. Whatever the air coming in the while flying, that is utilized for cooling of the all system. And that is, we just wanted to know that what should be the opening there. If you have a front end opening too much, that is also a problem because there is a drag. So aircraft efficiency will be decided on the basis of what is the kind of drag it is experiencing and all that. So that has to be optimized. So all these things is taken care, and finally whatever the opening you have, we did an optimization of the opening such that the whatever air is coming is sufficient to cool our TR module or not. That is what is found out. And when you produce the TR module, whichever the LRU, we put it on here, and we have different set of equipment. Basically, you have performance network analyzer, you have an oscilloscope, you have noise figure meter, you have power meter. So all these are required to completely assess the TR module function. You need to know what is the rise time, whether the device is falling in what, how much delayed and all that kind of thing, whether instantaneously it is falling or not. All that has to be checked. Then only we can, sort of accept that system. Otherwise, you have to go for a redesigning of the system. This is, we call it as the ATE, automated test system. So with the help of that, we'll do that. And this is a different combiner system. What we have is this, power divider combiner, we call it as, wherein a single input is made to distribute for 8 TR module or 16 TR module, whichever the way you want. That is achieved by this kind of device. So another device, what we have is basically from the front, I mean back end, we have a single source, single signal generator will be there. That is exactly fed to this system, and this system will subdivide into several output, and that will be fed to the power divider and all that kind of thing. This again further divides to for TR module. So we have this array, front end array is 160 by 8 element array. So all this 160 TR module need the RF signal to be bifurcated. That is achieved by several stages of this divider and combiner network. I told you this is a health monitoring and all that kind of thing. We inject the RF signal here, it made to pass through the particular TR module. We make the TR module active or passive, active or off. So that individual TR module I can control, and whatever information is there, it is picked up from the bidial and will observe between these two. So every path I can enable or disable and all that kind of thing, and find out whether that entire path is working or not working. And there is a single control for all this. So this single controller is again, I see there are so many, LRUs are there. All of them has to be operationally controlled. See, I'm saying that a particular TR module I want to enable or disable and all that kind of thing. So that is met through some controller. So that controller, the way we achieve is simple looks like, but they have a lot of IOs and all that kind of thing, which will be made to control the several systems. So we have for IFF, there is something called big controller in it. There is a monopus this thing, and there are sphere module of 160 numbers. ABF is something. So all of them are controlled through this controller. So you have IOs and all that kind of thing, which will make you to control the devices, control the LRUs and help in meeting the objective. And when you send a command from a central place, because everything happens from a central place, command has to go to the array, and the array has to perform according to my requirement. From the controller, whatever it is, decide what is the time taken for the entire thing. So the time I give a command from the central, but the whole configuration has to happen in the array. So that assessment is done, communication path delays, and so many devices are there in the path. What is the kind of response time of that device is, and some calculation is needed to be done in the, putting the phase shifter and attenuation values and all that. All that we found out that is 134 microsecond is sufficient for the communication. Once I give a command, by the time it get executed by the array is 134 microseconds. So that means within 134 microsecond or roughly zero point 0.1 millisecond, I'll be able to shift the beam. The main beam I can shift it to that order as such. So that is the kind of agility what I enjoy in having the active array. And I told you that power is required for operation of the TR module, and this is the kind of power system what you use. Every the power system will support the power requirement of 16 TRMM. That's how we configured and all that. And how the power is extracted is there is an auxiliary power unit. In the aircraft, we have generators. Along with the engine, there is a generator which that generated value will be converted into DC. It's a 9-phase, generator. It's not a 3-phase; it's a 9-phase thing, and that is fed through the ADRU. It will convert the DC, and through some distribution system, it will go to the all power supply and all that kind of thing. Again, power comes from the single point and get distributed. That the distribution system is shown here. And the biggest thing will come is I was telling you that return can come from the main lobe as well as the side lobe. Whenever the reflection happens from the target, it can come from the main lobe or a side lobe. How do you identify whether that return is coming from the main lobe? So we have something called a guard antenna, which has a coverage like that. It's a completely covering the side lobe level. So we observe the power received from the guard as well as from the main lobe. Suppose the power received in the main lobe is more than what you receive in the guard, then I declare that the power is, the return is coming from the main lobe. So the direction is very proper. And suppose it is other way, whatever is you are seeing in the main lobe is lesser than the guard, then I know very clearly it is coming from the side lobe. So we reject that. That is how we, avoid all the targets information which is coming from the side lobe. Yeah, I just skip all that. So we followed incremental integration. The entire box has so much of complexity of cable. It's the kind of cables what you use is almost 3 kilometer length of cable. So much of this thing is there. Because I need to have every element to be controlled. That is exactly our objective is. With the help of that, every element control, I can shift the beam in elevation as well as in the azimuth. That is the objective of meeting that. The kind of arrangement is done like this. So you have RF cable, you have power distribution, signal distribution the other side, and there's a power divider. Everything has to be put in that small box, whatever you have in the top. It is a very small box. It's a 7 meter by 1 meter by 1 meter, something like that. That's all in the size of the box, and all objective has to be met within that box. So the way we arrange, and finally what has to happen is that when I go for a maintenance of every LRU, I should be able to do that. So it is a plug and play. I mean, it's not hot swappable. I mean, when it is on, you cannot remove and do the maintenance and all that kind of thing. It's easy to remove and put it back. There is no obstruction for several of the LRU. That is how the design of it is taken care to meet the objective. And since it is outside the aircraft and it is subject to lightning and all that kind of thing, and when the lightning strikes, our system, I mean, our electronics should not get disturbed. So that study also we did actually, because whether that lightning strike gives a huge amount of current and all that, that current, whether it is going to affect my electronics or not, we checked. One we checked, we took a small antenna only, that is the dual segment we call it as. The back end, we have entire electronics. Once we did without switching on the electronics and check the TR module, whatever you have, whether it's functionally fine or not after the lightning strike. Another time we did, it's alive. I mean, the TR module was kept on. So at that time also we and everything was safe. So in that sense, we didn't have a problem. Yeah, our performance is evaluated in a PNFL chamber. We call it as a planar near field system. We call it as. Whenever you want to characterize an antenna, we need a sub chamber, an chamber kind of thing actually. Wherein we don't have external signal, I mean external radiated signal disturbing my measurement system. So for that we have an enclosed chamber wherein we have this kind of absorber, we call it as, and the antenna, test antenna, and there's a probe antenna. Both are kept in some proximity, there's some distance, and the distance between transmitter and receiver, or a probe and a DUT, is decided on the size of the antenna. So we call it as a 2d square by lambda kind of criteria. And the antenna, whatever you have, planar antenna, for that size, the amount of, I mean, the distance required is almost a kilometer. That is not possible to have such a big enclosed chamber and having that system. So we went to the different technology of assessing the, I mean, evaluating our antenna. This is called the near field system, and which met, I mean, wherein device and test is kept at very close proximity of the measuring antenna. So if this measuring antenna is moved in front of this up and down and in the x and y direction both, and we pick up the RF signal at regular interval. It's an Nyquist rate also we follow and all that kind of thing, and measure the RF signal, complex RF value, and then we do a near field to far field transformation. All this helps me to finally find out whether the beam is there or not, a radiated beam is there or not. So suppose I do, because so much of RF system is there. In the path, I showed the phase shifter, attenuator, LNA, or a transmit amplifier, and all that kind of entire path. All these devices have its own behavior, and it is not that this device, whatever I selected, is the same behavior shows for the other device, similar device. So it is a problem actually. So, and such kind of so many of them are 1280 element ke liye to so many TR modules being there and all that kind of thing. So first we check whether we have beam or not. We did a near field measurement. This is exactly plot of near field amplitude. This is a plot of near field phase, and you see there is no beam at all. It's just uniformly distributed. There is no main beam and all kind of thing actually. So when you did that, we call it the collimation process. We measure and correct them by appropriately putting the phase and attenuation value for the respective element. So when you do that, you see there is a uniform amplitude distribution and a uniform phase distribution, and you see there is a beam. So this is a main beam, and this is a difference pattern. We call it as a sum and difference is required for further improvising the angular accuracy. So the thing is 200 kilometer beam, we have 0.6 degree beam kind of thing, and which will show almost 2 kilometer coverage. So that is, you want to further improve the accuracy, azimuthal accuracy. You do use a monopulse concept, And these are the kind of pattern we have, azimuth pattern, elevation pattern and all that. And when it scanned, the kind of pattern what you have in the transmit and receive is shown here. And in 3D, it is like this. So the 30-degree angle scanning will be like that, and 0 degree like that, 45 degree. These are all command-based performance what is shown. And we have to do several pattern measurement is huge amount of is almost like months of work. And finally, when you put them all, I mean, all functionally together and all that kind of thing, and you see this is the target motion. So there is a control target, we call it as the control target will fly according to our need, and it did a maneuver and all that kind of things, a couple of maneuver like that, and finally it landed back, and the entire thing was captured very well by our radar. So this is the first, what do you call? We did the entire thing on a rooftop of our building, and checked the objective is met or not. After the confidence of this, we went for other flight trials. And in the meantime, when you put an antenna on any surface, the surface will also have an influence on the antenna performance. So there's a body effect, mounted antenna array, study we did. Forget about that. And why I'm telling is whatever the antenna we fixed, it will generate a distributed current on the surface of the aircraft, and this also will radiate. It's a secondary radiation we call it as. And without the body, the pattern is like this, and with the body, you see some deviation in the performance. So these are all essentials to be studied whether my location of the antenna is proper or not. There's a body effect is minimum or not. So that is exactly the one of the study what we did, And then we did a mounted on the aircraft. And when you mount on the aircraft, you should see that our power is 80 kilowatt. It's a huge amount of power which is getting radiated. It should not affect the other subsystem, whatever is there in the aircraft. So we have so many subsystems, I mean systems, system of systems, and so they should not get interfered. So that study also was done in the ground. And after mounting on the aircraft, flying at whatever the heights and kind of thing, and for a path and different target. Say this is called as a control target. The control target will carry its own GPS and all that, and will detect. So whatever they detected from us, we compare with the GPS position of the target also. And when it is coinciding, then we'll say that our radar is functioning to the requirement. And same thing when in the flight we found out a control target taking the maneuver and all that steady path. And there are several target being in the airborne. I mean, there's so many of them are there. Each one is a target. So whatever you see here, it's they're all target. So we are able to achieve the objective of a defined objective. So this is what I wanted to convey, that a huge amount of exercise is there from the concept to the realization. So that's what I wanted to share with you.
Participants, any questions is there?
Yeah, any questions?
Any questions? Any questions?
Sir, nowadays they're using spy drones.
Any?
Drones they're
Yeah,
using for
yeah,
spying.
yeah.
Can you identify?
This has a limit of, we have actually there is a flight aircraft called as Hawk that has a minimum RCS.
Yeah, that's
Okay, so the RCS is very low. That we can identify. Missile, some level, yes. Drone is a very small this thing actually is not with this kind of
Thank you all. Now I would like to call Wasim sir to propose the vote of thanks.
Thank you. Uh, a very good morning to all of you. First of all, on behalf of EPCET, I'd like to thank Dr. Venkatesh Rao sir for gracing this occasion with his presence and as well as for his insightful talk that we had right now. So thank you so much, sir. Next, I would like to thank uh, Srimati Ramadevi BL, Chairperson EPGI, Sri SV Pramod Gora sir, CEO EPGI, Sri SV Rajiv Gora sir, CEO EPGI, Sri Peter Francis sir, Secretary MG Charitable Trust, Dr. Prakash sir, Senior Vice President EPGI on his absentia, on the absentia. So next, I would like to thank our principal sir, Dr. Mrityunjay Vilate sir, and Vice Principal Dr. Yogesh sir, for his constant support that we have been getting throughout the tenure of this event. The event is taking place right now, so thank you for supporting us throughout the tenure. And as well as I would like to thank all the HODs, all the faculties, and all the student coordinators, as well as all the participants for their graceful presence on this very occasion. So basically, thank you all of you for coming over here, and it's a delight for all of us to welcome all the student fraternity from various colleges across our institute. Thank you so much. Thank you everyone. Thank you.